Group 16's challenge problem statement was based on the poisoning catalyst in methanol production. Industrial waste often gets into water supplies and environments in general, which is a dangerous threat to both people and the environment itself. Recently, electrochemistry has been used to make these compounds more manageable or completely get rid of them from the waste. Now, we're talking specifically about the copper catalyst poisoning the production of methanol from carbon dioxide. And what we want to know is the rate of the poisoning or the copper oxide production and at varying pressures and volumetric flows, as well as the concentration of both copper and the copper oxide poison using the given reaction kinetics. So the reaction kinetics that we are using are the chemical equation right there with copper and hydrogen creating methanol and water, and we have both our rates down there for methanol and the rate constants for methanol and the poison there with Km and Kp respectively. The reactor conditions themselves we set as having a fixed bed catalytic reactor that only contains water, carbon dioxide gas, the copper catalyst, and all of that flowing at a constant rate of 0.1 meters per second in solution for starting conditions. The copper is also assumed to be a mesh so that no mass transport issues come up when we are finishing this model. The reactor will not be well mixed in the axial directions, but it will be well mixed in the theta and radial directions because of the mesh assumption that we made, meaning no reaction happens until it reaches that point at least. The scale that we're considering is industrial, with the reactor being 400,000 liters and the reaction production rate being 2,500 metric tons of methanol per day. So with that information, we generate our model equations and the constants that we're going to use. So the production of methanol in the top right is shown as a varying nonlinear ordinary differential equations with variance in respect to the length of the reactor, which we assign to the z direction. And the poisoning of copper in the bottom right is based on both the length of the reactor and the time, since it needs time to react, and that is what the purpose of our poison rate reaction is occurring at. The constants over here in the bottom left have the velocity of our stream as stated before being 0.1 meters per second, and then the reaction or rate constant for methanol production and the rate constant of the poisoning production being 1 times 10 to the negative 3 and 1 times 10 to the negative 4 respectively. So to solve these, what we used was ODE 45 because they the methanol equations are all ordinary differential equations. The copper equations, however, are partial differential equations, so we had to reduce these into ODEs, and this helped us obtain smooth graphs that showed the relationships between the considered chemicals there. Our concentration profile is the results over there in our graphs. That is what we got from our code. The bottom graph is what our MATLAB code actually generated when we were creating this problem, and then the top graph is the ideal conditions and how they should appear and what we were kind of aiming for. The ideal graph was created to just show off what it really looks like and what we're supposed to be looking for rather than just giving the data as is. And it shows that as the methanol production goes up steadily, the reactants go down exponentially, which is very close to the model and how that, the relative rates. The concentrations of both hydroxide and copper go down slightly as the hydroxide either blocks the copper and creates the copper oxide or reduces into water. Now, if both the length and time were to increase, the ideal conditions would show that the rate of methanol production should stabilize and kind of plateau out. Now, looking at our models, we can see that the copper catalyst over the length of the reactor and the time that it is in reaction directly relates to the concentration over the reaction time and length of the reactor at steady state velocity. Observing the ideal case, copper and hydroxide concentrations decrease linearly while the methanol concentration increases logarithmically until it hits that asymptote where it stabilizes. And the carbon dioxide and hydrogen concentration decrease exponentially until they reach zero, determined by the length of the pipe that we defined at steady state with the stream velocity, as it has to give time for it to start reacting. This model did fail, however, and it is likely due to either the simplicity being too simple, the linear relationships of concentrations being either incorrect or maybe they were nonlinear, and we may have used improper modeling form for this case and something may have worked a little bit better. So we hope next time we can get this down and have a more accurate result. Thank you.